Hey, this is Matt once again. What about to the video? This is another paid request, this time for Jacob. And for those interested in requesting pretty much any type of videos, or topics, or reactions, or reviews, or re-reviews, a list, a ranking, a topic, article, whatever it may be, you'll look at article, whatever, pretty much feel free to send it either directly to my PayPal or join my Patreon. Both links are down below in the info box. Now, he is the same person that had sent in requests for you to react to other teaching lectures on either physics or black holes or the like. It's obvious I'm not really into this stuff. It's cool that Jacob, thank you for that. It's cool that you're into this stuff. I'm obviously not the type of guy who's into this stuff. So, I don't know what to say. And this is like 2 hours long, so we'll do this. I will watch this for 20 minutes and then flip through. Otherwise, it's just going to be me silently sitting here watching and not really commenting or anything, because there'd be nothing for me to comment on, because the subject matter, in this case, modern physics, quantum mechanics, lecture 1, it's going over my head, back into the closet, buried with that weird dummy from Making Contact. For all two of you that get that. But with that said, let's go with it here. SOIT, Stanford on iTunes.
This program is brought to you by Stanford on iTunes U at Stanford University.
Well, what she
Please
says.
visit us at itunes.stanford.edu.
You say so.
I just want to do one thing actually before we start the material of the class. A whole bunch of people, a lot of people, particularly people from Europe who actually follow these things on the internet, seem very puzzled. They send me email, even some of my friends in Europe who are physicists who are following it, are very curious about what's going on here. They don't see you people, they only see me. And they know that I'm teaching a class in this or that special topic in classical mechanics or whatever.
Yeah.
And they can sense that there's something a little bit different about it. They can sense that it's not a standard undergraduate or graduate course in these subjects. And they ask me, what is this? What is this about? Or who are these people you're teaching to? They can tell it. And most of them don't know what continuing education means. They didn't know what it meant. And so they asked me. I thought I would tell them over the internet what this class is. It's continuing education, which means education for people not from Stanford, people not, they can be from Stanford. Some of the people probably are either employed by Stanford, maybe were students at Stanford, but almost everybody in this class is a little bit too old to be an undergraduate student, even a little bit too old to be a graduate student. They're people from the community, from Palo Alto, from Mountain View, from, who lives further than Mountain View?
Too old to be a teacher.
Okay, what's the furthest you come for this? Where? Foster City. Okay, so that's 20 miles away. So people from within a certain radius, I don't know, whatever the radius is, are allowed to come and take courses at Stanford. They pay a bit of money for it.
Or from the quantum
and
zone.
The professor teaches them. Now, this is not, it is most definitely not your standard freshman physics. There's another guy on the internet who teaches freshman physics, and totally does it very well. That's not what this is. This is the real McCoy, theoretical physics at the full-scale level. We use equations. We not only use equations, we sometimes use hard equations, but we tend to try to use the simplest equations that will do the job. Basically, we try to keep it minimal. Just out of curiosity, I more or less know the answer just by looking. but what the age distribution of people here is by comparison. Is there anybody here under 40? Yeah, there's maybe one handful of people under 40. Incidentally, for those who can't see the audience, there's probably about 100 people in the room. I'm not sure. It's a small theater with a lot of seats. It's a lecture theater.
One person
More or less
under
filled
40.
up. And maybe 4 or 5 or 3 or 4 people were under 40.
3 or 4.
Let's see. Let's go to the other end. How many people here are over 70? A good deal more. Maybe 10 or 12. Anybody over 80? We got a couple of people over 80. Anybody over 90 this time? Oh, there have been people over 90. There have been people over 90 in this class. So you see the age distribution is such that basically people want to get to the basic ideas fast. They don't have a hell of a lot of time. They want to get there fast. So I try to tell them in some minimal way what the basic things you really have to know in order to get on to the next thing. Sometimes the basic things that you need to know are a little more difficult, a little more elaborate. We do them anyway. We do them as efficiently and as straightforwardly and with the minimal amount of stuff to get them right, to get them really right. Not metaphor, not analogy, but equations when necessary.
Well, it still loses me, though.
What else can I say about this class?
It still loses me.
I guess it has various names. Quantum mechanics, the Physics 25. I'm inclined to call it quantum mechanics for old people, including myself.
Quantum mechanics for geriatrics.
Anyway, the first course in the series, let me just say what the outline of the whole course of courses is. These series of courses will consist of about 6 10-lecture series. The first of which was in classical mechanics. The classical mechanics is the basis of all classical physics. Classical means before quantum mechanics. Anything that doesn't involve quantum mechanics, or which ignores quantum mechanics, or which is in a range of parameters where quantum mechanics can be replaced by basic classical logic, that's called classical physics. Mm-hmm. So the first class was classical mechanics, which is in some sense the basis for all of physics, the motion of objects, the energy of objects, the momentum of objects, what the characteristic behavior of systems is as they evolve with time, and so forth. We discussed that last quarter, and anybody who is thinking of following these classes should begin with that. The next class, which is already on the internet, was called, I believe, Quantum Entanglement. Now, this is also a class on quantum mechanics, and it will be self-contained, but I would strongly advise anybody who's following to go to course number 2. Was it called Quantum Entanglement? Does anybody remember? I think it was called Quantum Entanglement. It is also on the internet. It was the first one that was on the internet. And to get that under your belt first, before attempting to do the full-scale quantum mechanics that we're going to do here, although what I'm going to do is pretty self-contained. I'm going to start this evening with some basic thoughts about the deep differences in the logic of classical mechanics and quantum mechanics. Mm-hmm. Well, classical, maybe even mechanics is too strong a word. Classical physics and quantum physics. There are some very queer phenomena in quantum physics that don't exist in classical
Right,
physics.
there's what?
And quantum physics. There are some very queer phenomena in quantum.
You can't say that word anymore. The Q to the U to the EER. You can't say that anymore because people will get upset and cancel you. Be careful, Professor George Carlin.
Quantum physics that don't exist in classical physics. Now, one of them is the fact that quantum mechanics is based on statistical thinking, randomness, a certain degree of, not imprecision, that's not the right word, a certain degree of non-deterministic or indeterministic behavior, unpredictability, that's the word I'm looking for, unpredictability, but it's a special kind of unpredictability.
Sure.
Einstein famously said, God does not play dice. Niels Bohr told him,
He plays billiards.
Einstein, don't tell God what to do. But in fact, in a sense, God, I don't know if he's a God.
He plays
I use
jacks.
the word God in the same sense that
He's
physicists
got the
always
jack.
use it, meaning the laws of physics or something like that. The laws of physics don't play dice, at least not in the standard sense.
They play charades.
Let me imagine for you a theory that's based on a bit of statistics, which is not the way quantum mechanics works. And then I'll illustrate it for you by showing you some of the differences. Imagine that there was an element of randomness in Newton's law.
Fifth element?
Whatever, which law? F equals ma together with the law of gravity. All right, so F equals ma together with the law of gravity
Starting Sandra
tells
Bullock.
us how objects move, let us say how the moon moves around the Earth. And it predicts with infinite precision, if you could work out the equations with infinite precision, and if you could account for every detail of the Earth and the moon and all the material that's in between and so forth, it would predict with enormous detail, deterministically, the motion of the moon.
And this is how we do
Which means
Apollo
if you know where
13
the
back
moon
to Earth.
starts, and you know how the moon is moving in the beginning, then you can predict forever after exactly how the moon moves around the Earth. That's the deterministic classical mechanics.
Oh, it looks like
Now
a cantaloupe to me,
imagine a
Professor Carlin.
modification. And the modification involves a little bit of randomness. For example,
It looks like a
okay, so let's
one
imagine
nipple.
God sitting on
breast.
his throne, throwing dice. Every tenth of a second, God throws the die, and if he gets snake eyes, what he does is he gives the moon a little extra push in one direction. If he gets a 7, he pushes the moon a little bit in the other direction. A degree of randomness based on the random throwing of dice, and a really random number generator being used to put a little bit of fluctuation into the motion of the moon. That sounds like it introduces the kind of uncertainty, the kind of thing that one talks about in quantum mechanics. Uncertainty, non-predictability, unpredictability, but it is not anything like the randomness and unpredictability of quantum mechanics. The randomness and unpredictability of quantum mechanics is exceedingly special. Exceedingly special.
Sorry, itching my foot if you're wondering what the hell I'm
It's
doing.
that we want to get our head around and learn and understand the difference between these things by the time this class is finished. But also we want to learn how to use quantum mechanics a little bit to calculate some things. Let's notice one thing about this law, which includes a little bit of randomness. The throwing of dice in order to either kick the moon a little bit or inhibit the moon's motion a little bit. One of the things that would do is to add a little bit of energy or subtract a little bit of energy from the motion of the moon randomly. If you randomly give the moon a knock this way, and then a kick that way, and a bonk that way,
They're playing
doing it
kickball.
over and over again, each time you do it, on the average, it may not change the energy, but each little increment is randomly going to either increase the energy or decrease the energy of the moon. And if you do that randomly, eventually that will build up to a statistical randomness in the energy. In other words, energy would not be exactly conserved in a world in which the laws of motion included a little bit of classical randomness. I call it classical randomness to distinguish it from quantum randomness. In quantum mechanics, You prepare a system the same way that you might prepare the moon in an initial situation. You let it go for a while and then you look at it. And indeed you discover at the end of it
Discover a guy almost walked into the shop.
Unpredictable. But you also find that energy is exactly conserved. No hint, no remnant at all of energy being knocked this way and knocked that way. If you start it with a given energy, with a given precise energy, and you let it evolve for a while, and you measure the energy later, the energy is exactly the same as you started with. So there's something funny about this randomness. It seems to affect some things and not other things, and doesn't work the way you might expect randomness in classical physics to work. Let me give you I think three other examples of the oddness of this randomness. The first comes from an experiment which, to my mind, shows the weirdness of quantum mechanics in the easiest and
All I've gotten is shit's random.
difficult way. Much easier for my money than Bell's inequalities and all that sort of stuff. It's called a two-slit experiment. All of you know about it, or most of you know about it. If not, you learn about it right now. But it is extremely odd when compared with classical randomness. Classical randomness just being this idea that every now and then you give the system a little knock. The two-slit experiment
Knock on heaven's
a
door.
source of particles. Those particles could be photons, they could be electrons, they could be neutrons, they could be bowling balls, except the effect for bowling balls is so minute that you'd never be able to measure it. So when we
What about
speak
photon
particles,
torpedoes?
we think about things which are very light, and because they're light, the quantum effects associated with them are significant and measurable. All right, so we have a source of some kind. It could be a laser.
Source. I
shooting out
hope that
photons.
highlighted the source. I hope
Imagine the
not.
photons are coming through one at a time, very small number of them, quanta of light.
Photon torpedo
one at a
shoots
time,
out.
one
It
at a
destroys
time,
the
one every 5 minutes.
Christopher
if you like.
Plummer
I'm
from
just
Star
gonna
Trek
go through
6.
some extreme situation.
To be or not to be.
Photons coming out of the photon gun, and the photons pass through a obstacle with a little hole in it. All right, this is a two-dimensional diagram of a three-dimensional situation. This blue object over here is intended to be
It's supposed to be blue?
with a tiny hole in
I can
it.
barely fucking tell it's supposed to be blue.
Photons, they go through, and they come out the other side of the hole. And when they come out the other side of the hole, they eventually get to a screen over here. That screen records the photon by a flash of light at the screen. Not the flash of the original photons, but another flash of energy appears at a point on the screen and records, or it could be just the blackening of a photographic plate, something that records the position of the photon when it goes through here. Now first let's think classically, but classically with a bit of randomness. The bit of randomness that we can imagine is that when the photon goes through here, a little random kick might influence the photon and either kick it upwards or downwards. In fact, by a random amount. What would we expect then? Well, if there was no randomness, then the photons would go straight through and illuminate a single point. Be completely deterministic, the photons would always arrive at exactly the same point, if the hole was small enough.
That's like Yar's
and
Revenge.
the beam of photons was narrow enough. But now we can imagine a random kick. What does the random kick do? Well, it changes the direction.
Random kick in the nuts hurts you.
Photon. Not the whole photon beam, but one photon at a time. It might kick the first photon up a little bit, the second photon down, and so forth and so on. Eventually, what you will see is a blob of illumination on the screen over here.
The original or remake blob?
The photon might go straight ahead, so the blob might be most intense at the center. It might
Well,
be
the blob
highly
must be Steven
improbable
Seagal.
to knock the photon through 60 or 70 degrees.
That's Steven Seagal trying to
So the
hide
signal
now
would
behind
fade as
a
you move
door.
away from the center.
And his stomach just gives it away.
With a maximum intensity
Steven
in the
Seagal,
center
you fuck.
and thinning out as you move far away. And you might describe it by a probability function. The probability function being the probability that the
That one looks
photon
like if an
arrives
egg had an
by some
eyeball.
Now we go, now we do the same thing in real quantum mechanics, in other words, in the real world. We see essentially the same thing. The photons go through the hole with no ability to control the situation. We find out that the photons again create a blob like this. But now we're going to do something a little different. And I think everybody here, more or less everybody knows what I'm going to do. I'm going to open a second hole. Okay, but let's think about what classical randomness would do. Classical randomness would simply mean that, and we'll also imagine that this beam of photons is at its origin a little bit uncertain and a little bit random, so that some photons begin a little bit upward, some photons a little bit downward, some photons go through the upper hole, some photons go through the lower hole. If a photon goes through the upper hole, it may or may not get a random kick and get knocked off course. If it goes through the lower hole, it also gets a random kick. Now we're imagining the photons come through one at a time. We could even imagine okay.
What happened?
I do that all the time. Where was I? Yes, the photons get a kick. We're imagining that the photons come through one at a time, very sparsely.
Maybe someone fell asleep.
What one
I
photon
was about ready to.
doesn't influence a later photon, because the later photon comes through so much later that whatever gave the first photon a kick is already finished happening, and it's waiting for the next throw of the dice. In fact, the next photon may come through 100 throws of the dice later, and so we expect the next photon to be random, statistically independent of the first photon.
Well, just fire the goddamn photon torpedoes, Professor Carlin.
Well, let's decide what we would expect. Supposing only one hole is open, if only one hole was open, then we would see a blob of illumination like that.
Hello, Steven Seagal.
Might look something like that. Supposing we closed up the first blob, the first hole, and the second hole.
There's a second hole.
What happens if we open both holes? What happens if you open both
That the
holes?
girl's having a good time.
Mechanics is the probability for a photon to get to the screen at any given point is the
Oh, a
sum
three-way.
of the probabilities for it to get there bits. You would always see the signal over here.
Yeah, you always see Steven Seagal because he takes up, he's the eclipse for the Earth.
And it would look, I wish I had another color. You never leave me enough colors. All right.
Or brown.
We would see something which would look like
A penis?
just a higher. No, it would be much bigger than that. Ability would dictate for a series of particles coming through here, one at a time.
Was it Yellow Submarine?
In particular,
That was a bunch of dudes.
well, first of all, what is this figure? This figure is a probability distribution.
It's a lot of people with a bunch of iron rope.
Horizontal axis here tells you what the probability
It's
of
probably Steven Seagal and his butt
particular
boys.
point at a particular height here. All of a sudden, no photon gets to that point. Even up some phenomenon of interference of its works and how the logic, the coin which can either be heads or tails. Now, of course, flipping the coin, that introduces a level of uncertainty, a level of
Chance.
statistics, probability into things. I want to think about the deterministic laws. The truly deterministic laws are the ones that whatever the coin is doing, it will tell you what the coin is doing next. So when we discussed this last quarter, we talked about two possible laws of physics. The first was that if you find heads, in the next instant, when you look at it, after an instant of time, you'll find heads again. If tails, then you find tails again. Then your laws of physics just permit two possible
Or you find tails and you find
evolutions.
Sonic.
Heads, 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 or tails, 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 tails. And the other possible laws of physics,
I'll take
law of
head, head,
physics,
head, head, head.
was that when you see a head, in the next
As long as her
instant,
teeth don't hurt.
microsecond, or whatever your unit of time is, you will see
Oh,
the
you know,
opposite,
10
tails.
minutes.
Then the two possible laws of physics are the two possible, not laws of physics, the two system was a die. Let's consider a simple law of physics. A simple law of physics
HTF.
will tell you that whenever you have heads, it goes to tails. Whenever you have
Holy
tails, it goes to
Toledo,
feet.
fat
Whenever you have
man.
feet, it goes to heads again.
Must be talking about Steven Seagal
Then,
again.
wherever you start, you just cycle around endlessly forever and ever. Now, there's a
Play
certain
keep
sense
away with his
in which this
paychecks.
is in which
Try to get
this is-
Seagal to run it
what does
off.
mean to say it's deterministic? What does it mean to say information is not
How big is
lost
Steven Seagal's
in this
ego?
process? What it
And what's the
means
percentage of it changing to
that-
not changing?
no matter how long the system evolves, in other words, changing the direction of every arrow.
The reason Seagal acts the way he is, he has 3
Actually,
periods.
you could really do this by pressing a button.
Which is
Change
weird,
the law
because
of physics.
women have
if you
1 per
allow
month,
the
but
system
Seagal
to
has 3 per
evolve
month.
For any
And it's very
length of
strange
time,
biology.
At the end of that time, for the same exact length of time, you'll come back to the starting configuration. Now, to do that, you might not even need to know the laws of physics.
You need the
You might
Book of
need
the
to know
Dead.
Very little. Now, what about a little bit of classical probability? A little bit of deity playing dice. So let's suppose
Play jacks
there's
instead.
some- then run it backward. We'll go
Rewind.
back to the same point. But if you, in other words, this test will fail. It'll fail.
On the F-steel of fuck.
Is information lost? Well, there is an element of statistical things in quantum mechanics. A little bit. And you might think that this is more or less like...
It's a worm, it's Scotty Too Hotty.
In fact, we'll find some go up, some go down, some... But now, let's ask the following question. Supposing after a period of time, we send an electron through, one electron, after a certain period of time...
He meets a neutron, does the
given
neutron
enough
dance.
time to do this, is there really a button that you can push? Is there really something that you can do to a system that will reverse the motion? Yes, in many systems there is. Does that electron, we're not going to look at it, but do we later, after the end of the experiment,
Do we fuck it?
it either gets knocked down or knocked up?
Knocked
Which is
up.
it?
That's
Does
what
it-
happens to her too.
Does it? The answer is that if we don't look at the system in the intermediate stage after it's gone through the hole over here, don't look at it means don't interfere with the electron in any way. Take that screen away that might have converted that electron into... What if somebody does look at the electron when it goes through to the side over here?
They're not
For
down.
example, it's okay, it's only a Chilean peso. I lost my Chilean peso. I think it was actually 100 pesos.
Go back to Mexico
Here's
and
my
get him.
Chilean peso. You can look at an object and determine its state, determine the heads or tailsness of it, to the same, do anything to detect the object. The reversibility will fail. Check the system, measure the system, remembers which way the electron went through.
This is how you
In
play
other
Yard's
words,
Revenge.
there's some gas molecules in the apparatus, whatever it is, in such a way that something records which way the electron is destroyed, and the answer
See,
is
secretly,
exactly the
this
same
is how
as
to play
possible.
Battletoads.
Answer, namely the property of quantum mechanics, that you cannot do measurements on systems without disturbing them. Imagine that we have talked about the uncertainty principle. That's a sophisticated question, so I suspect you thought about
Oh, the
it a little bit.
photon on the
If
left is
the position of
coming.
this detector, the up-down position of this detector, delta X, is very, very small. That means
Delta
the
theta phi.
uncertainty in the momentum of the detector is large.
See, it's
Okay.
coming.
That
It's
means if I were
pissing.
to plot the probability. But unless the probability distribution has been shifted by something approximately equal to its width,
then it's a humpback whale.
Explain the strength of quantum mechanics that way and so forth, and so it was laziness that didn't allow us to get the position and the momentum. Deep protecting its position and its velocity, known by Einstein. Now, here's another fact about a beam of light. Beams of light have not only energy, but they also have momentum. You can take a beam of light and shine it on something and it will warm it, it will heat it. That tells you it has energy. But you can also take a beam of light and you can shine it at that door, and if the beam of light has sufficient intensity, it'll just push the door open. In other words, the beam of light...
It's weird how the audio just changes randomly.
So that when the door absorbs the beam of light, the door takes a kick. Just as if you threw a ball at the door, and the door collides with the ball, it has momentum. Okay, now what is the relationship between the energy of a beam of light and its momentum? I'll just tell you what it is. This is classical Maxwell theory of light. If a beam of light moving in a particular direction, assume it's moving in a particular direction, has energy E, then it also has momentum. And the relationship is that the energy is the speed of light times the momentum. Incidentally, let's just check the units of that equation in another way. Let's compare that with Newton's theory of momentum and energy. For an ordinary particle, the energy of the particle times the momentum. That's what lambda is. So it is equal to lambda divided by t, which means lambda large golf ball. Doesn't matter. If he wants delta x to be smaller than a centimeter, then he's got to be using a wavelength smaller than a centimeter. But if he's using a wavelength smaller than a centimeter, that means the momentum of the photon has to be larger than h over 1 centimeter. So the smaller delta x, the larger the momentum of the photon.
It sounds like I'm hearing calculations to go find Godzilla to fight Monster Zero on Planet X.
That he has to use to make the impression hard.
I'm sorry, folks. I have to do it this way. I'm sorry, Jacob. I have to do it this way. There's just no way I can sit through an hour and 50 minutes straight of this type of stuff. It's just... I'm not even doing it for exaggeration. I watch and listen to it, and it like makes me physically tired. I don't know if it's my brain just trying to overwork on stuff, or short-circuiting, I don't know.
The reason is because light doesn't come in discrete packets.
Nothing against this professor. I mean, all jokes aside, seems like he's a nice guy, very intelligent, easygoing delivery. I give credit to that. Seems like a good teacher. It's just the subject matter, not for me.
We've used the fact that light comes in discrete, indivisible quanta, discrete, indivisible photons. And if we have a wavelength, then there's a minimum amount of energy out of classical mechanics with such good,
Not all is
with
different.
such a good determination. Okay. So the velocity very much. You'll never be able to come back to you. Or 1, 2, 3, 4, 5, 6 for a die.
But 7, 8, 9.
In
Because he was hungry.
mechanics, or mechanics for heads and tails, or a bunch of p's and x's for a general system of many particles. And in order to, it's not a set, but it is a vector space. In ordinary maps, or Schmechter's, but in a pointer, if you like. complex number. If you have two vectors, a vector, an abstract vector by
Victor,
any
vector?
complex
What's your
number,
vector, Victor?
and you get a new vector.
Roger,
It's an
Roger.
operation that you can do. And the next
What's your
operation is that you
vector?
can add any two vectors.
Sorry, I'm not thinking of an
Now,
airplane.
of course, if you can add any two vectors, and you can also multiply them by complex functions of one variable. For simplicity, that's a simple. If that means multiply a vector by n. Also define them, and you get what I compta. That's an operation that you can do. States times head.
Wait a minute.
Let's call them A and B. You can add them, and you get another vector. So adding vectors give new vectors. Now, first of all, here's something which is really, both of these things are really new when you go from classical mechanics to quantum mechanics. Imaginary part, illustrating these numbers, arbitrary complex numbers, 2, length 3, length 4, and such a column in making mumbo jumbo. No, I think I've given you rather accurate definitions that you can understand of what vectors are. So much mumbo jumbo. But at the moment, we're doing abstract mathematics. Any other questions? Okay, so let's continue with the abstractions.
Did someone call him mumbo
It's best
jumbo?
that we go through vector spaces once and for all. It's the basic doesn't operate. Okay, sorry. And that theory was and allows you to ask allows you to combine concepts together. And or all these ideas have some meaning in set theory was and as you take two sets and you combine them and make the union of them, or you take the intersection. Or is it the other way? It's the other way, isn't it? It's the other way. Sorry. And is the intersection, or is the...
Even he's getting confused about it. I don't blame him.
The analogous logic in quantum mechanics doesn't operate on sets, it acts on vector spaces. So it's best that we go through vector spaces once and for all. It's the basic underlying mathematics, and once we get familiar with it, it won't seem so much mumbo jumbo. But at the moment, we're doing abstract mathematics. Any other questions? Okay, so let's continue with the abstractions. Now, in the x squared is and if you're not, most of you, of course, are quite familiar with complex conjugation. I want you to think of it as a very, very basic operation.
Sure.
But
I don't even know what you
I want
said,
to think of it
but
as a mapping of the numbers.
I think it was English, but...
Given any number, any complex number, you can map it to its complex conjugate. What about vector spaces? I think we should probably quit now. I think it's time to quit now. Next time we'll go through a little more about vector spaces, operators,
I know Vector Man for
addition
Genesis.
operators, and eigenvalues. And then we'll begin applying it to quantum mechanical problems.
The preceding program was brought to you by Stanford on iTunes U and is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at itunes.stanford.edu.
Right. If you say so. Come on. That in there. I don't know what to say. Yeah, I don't know what else to say. I really do appreciate it, Jacob. I appreciate your kindness. I appreciate the kind gestures. I apologize. It's just, if I really did sit there minute by minute, I would not be able to really say anything of note. I would just be sitting there silently, kind of just going, I don't know what I'm supposed to say. I don't know what I'm supposed to do. I feel discombobulated, confused, tired, all the above, and I'm like, I really don't know what to say. I guess I could mention one second. Where was it? Oh. Jacob's definitely into this stuff because he said, shit. I have his message here. Why am I not finding it? I have it here. Where the hell is the thing? Where the fuck? Sorry, my email's messing up. What the fuck? Okay, fine. Maybe it's for the best, just maybe he doesn't want me saying what his message, but it was a very nice message. Talking about how he's interested in this, how it's a subject that intrigues him, which is cool. Like I said, it's just not for me. It's not. Hey, we're all into different things. There's nothing wrong with that. We all can't be into the same subject matter. It's just, again, I know it's for the whole hour and 50 minutes, but it just to a point where I'm like, this is just going to be a very boring video where I'm just sitting there silently going, and just cut to Homer Simpson doing the same look, and then in his head and in my head it's the Monty with the symbol. So, but hey, with that said, thanks for watching. Thank you once again, Jacob. Take care, guys, and we will see you later. Bye-bye.